You think you know comets. Ice, dust, pretty tails pointing away from the sun. Simple physics from your high school textbook. Then 3. I-Atlas reaches 1.36 astronomical units from the sun on October 29th, 2025. And every rule breaks, not breaks quietly. Breaks loud. This thing is racing at 58 kilometers per second from another star system. Third interstellar visitor we have ever confirmed. July 1st, 2025, Atlas telescope in Rio Hurtado, Chile catches a faint smudge moving through Serpens Cauda near the galactic plane. Magnitude 18, 4.51 astronomical units out. They run the numbers and the orbit screams hyperbolic. Eccentricity 6.144. That number means one thing. This object is not coming back. It formed somewhere else, got kicked out, and has been drifting through the Milky Way for billions of years before crossing our path, 325 million miles from Earth when spotted. Moving through dense star fields near the galactic center where most surveys would have missed it entirely. Within one day, they have 122 observations from 31 observatories. Pre-discovery images go back to June 14th from the Zwicky Transient Facility and 3 Atlas telescopes worldwide. The comet had been in our sky for weeks before anyone noticed. Amateur astronomer Sam Dean finds frames from June 5th, showing the same fuzzy dot nobody recognized as alien. It was hiding in plain sight in the densest part of the Milky Way where millions of stars blur together. If you value documented cosmic chemistry and deep-time planetary science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from the Astrophysical Journal Letters paper by Martin Cordner and team published September 26, 2025, reporting James Webb Space Telescope NIR spectroscopy showing the carbon dioxide to water ratio of 7.6:1, and from ArXiv preprint 2510.25035 by Chi-Ching Zhang and Carl Battams, submitted October 28, 2025, documenting rapid brightening observations from Stereo A, SOHO, and GOES 19. Chronographs showing the comet turned bluer. Then the sun near Perihelion with brightness scaling as heliocentric distance to the negative 7.5 power. These are peer-reviewed or pre-publication institutional sources providing the chemical composition data and perihelion behavior measurements. Now back to the information. The name tells you everything. 3I, third interstellar. After 1, I Oumuamua in 2017, that cigar-shaped mystery that appeared, accelerated weirdly, and vanished, and 2, I Borisov in 2019, which behaved like a normal comet, but came from somewhere else. 3, I-Atlas is different, bigger, stranger. Estimated nucleus between 320 meters and 5.6 kilometers across. Most likely, under 1 kilometer based on Hubble images from July 21st, 2025, taken when the comet was 445 million kilometers from Earth. But that size estimate is shaky because you cannot separate the nucleus light from the coma light. The thing is already active, already outgassing, already breaking the pattern. Early observations from NASA's Transiting Exoplanet Survey satellite from May 7th to June 3rd, 2025, when the comet was 6.4 astronomical units from the sun, show it glowing bright even at that distance. Water ice does not sublimate that far out. Whatever is driving this comet is not water. The Gemini South Telescope and NASA Infrared Telescope Facility confirm water ice in the coma on July 5th and July 14th, but it is a passenger, not the driver. The Swift Observatory on July 30th and August 1st detects hydroxyl ions and water vapor, weak signals compared to what comes next. August 6th, 2025, James Webb Space Telescope points its near-infrared spectrograph at 3I Atlas. Heliocentric distance 3.32 astronomical units. The spectra come back, and Martin Cordner at Catholic University of America sees the numbers. Carbon dioxide dominates, not by a little, by 8 times. The CO2 to water ratio sits at 7.6 plus or minus 0.3. Among the highest ever recorded in any comet. Solar system comets average far below that. Long period comets and Jupiter family comets cluster lower. This ratio is 4.5 sigma above the trend. Statistical language for this does not happen by accident. The coma stretches with enhanced outgassing toward the sun. Carbon dioxide at 4.3 micrometers, water at 2.7 micrometers, carbon monoxide at 4.7 micrometers, carbonyl sulfide tentatively detected. Dust scatters light at 1.2 micrometers, but the gas emissions are what matter. The production rates measured across different distances from the nucleus show carbon dioxide venting at massive rates while water stays suppressed. Not just suppressed, Weird suppressed. The coma should be steaming water as it nears the sun. Instead, it is belching carbon dioxide like an industrial accident. 150 kilograms per second total mass loss. 87% carbon dioxide by mass. 9% carbon monoxide. 4% water. That is not a comet composition. That is an alien chemistry factory. The SphereX mission observes from August 7th to August 15th, 2025. Detects a carbon dioxide gas cloud extending at least 348,000 kilometers from the nucleus. The size of the cloud matches measurements from GOES 19 CCOR1 coronagraph near Perihelion, showing a coma 4 arc minutes across, roughly 300,000 kilometers. This is not a small comet quietly sublimating. This is a planetary-scale chemical event happening in real time. By August 23rd, the Very Large Telescope in Chile is tracking it with both X-shooter and UVES spectrographs. They are not looking for ice, they are looking for metals. Nickel first detected July 20th at 3.88 astronomical units from the Sun. Distance where metals should not vaporize. Nickel melts at 1,455 degrees Celsius. Vaporizes at 2,913 degrees Celsius. At nearly 4 astronomical units, the solar heating is nowhere near enough. Yet the nickel emission lines are clear. Atomic nickel vapor streaming into space, 3.9 grams per second of nickel. Not much in absolute terms, but the presence is what matters. Rohan Rahatgaonkar leads the VLT team, and they keep watching as 3I Atlas approaches the Sun. July to August, the nickel emission explodes, 25-fold increase in 1 month. The closer it gets, the more nickel pours out. By August 14th, cyanide shows up too, 17.6 grams per second. The Nordic Optical Telescope and Southern African Large Telescope join the observations. All of them see the same thing: nickel without iron. Every natural space object ever studied shows nickel and iron together. They form together in supernovae. They exist together in asteroids and comets in predictable ratios reflecting cosmic abundance. But 3I Atlas shows nickel emission and no detectable iron lines. The VLT looks for iron, doesn't find it. The MDM Observatory looks for dicarbon and tricarbon, doesn't find them. The James Clerk Maxwell Telescope on September 7th detects hydrogen cyanide production at 1.5 times 10 to the 25th molecules per second. By September 14th, it climbs to 4.5 times 10 to the 25th molecules per second. 2 kilograms per second of hydrogen cyanide. August 24th, Keck 2 telescope in Hawaii with the Cosmic Web Imager captures narrow-band images. Nickel emission at 0.3865 to 0.3885 micrometers. Cyanide emission at 0.3605 to 0.3625 micrometers. The nickel is concentrated near the nucleus, exponential radius 600 kilometers. Cyanide spreads wider, 840 kilometers. Both show asymmetric profiles extending toward the Sun and away from it, an anti-tail pointing sunward. Comets don't do that. Dust tails point away from the Sun because radiation pressure pushes them. Ion tails point away because the solar wind pushes them. Anti-tails are rare geometry effects when Earth crosses the comet's orbital plane and we see the dust sheet edge on. But 3I Atlas shows gas jets pointing at the Sun, not dust, gas. The Hubble Space Telescope on July 21st, 2025, resolves the nucleus and coma in high detail. Teardrop-shaped dust cocoon, anti-tail structure confirmed. The nucleus appears drop-shaped with dust streaming in both directions. 0.32 to 5.6 kilometers diameter range for the nucleus, with most likely value under 1 kilometer. The coma brightness accounts for a large fraction of total apparent brightness, meaning the actual solid nucleus is small and the activity is intense for that size. Astronomers propose nickel tetracarbonyl, industrial chemical used in the MON process to refine nickel on Earth. Colorless toxic gas that forms when nickel reacts with carbon monoxide under specific temperature and pressure. Breaks apart easily when exposed to ultraviolet light, releasing nickel atoms and carbon monoxide. The hypothesis: organic compounds containing nickel in the comet's nucleus decompose under sunlight, releasing atomic nickel vapor far from the Sun, where thermal sublimation of pure metal would be impossible. If you value documented cosmic chemistry and deep-time planetary science like this, subscribe. It's the best way to support our work. Now back to the information. But that leaves questions. Why no iron? Iron and nickel are cosmic twins. If the nucleus contains nickel-bearing organics, it should also contain iron-bearing organics. Unless the formation environment was weird, unless something about where this comet came from had conditions that separated nickel from iron chemistry, or unless detection limits matter. The telescopes used have specific sensitivities. Iron emission lines might exist below the threshold. Most scientists say don't jump to artificial conclusions yet. Natural explanations remain on the table, even if they require invoking chemistry never seen before. Thomas Puzia at Pontifical Catholic University of Chile says we just cracked open the door to a whole new world of chemistry we never had access to before. That is the conservative take. The thing is natural, but so exotic we have no reference frame. Martin Cordner says the carbon dioxide to water ratio suggests 3I Atlas either formed near the carbon dioxide ice line in its home protoplanetary disk or underwent extreme radiation processing during interstellar transit that stripped volatile ices and left a carbon dioxide-rich surface layer. Both options point to conditions radically different from our solar system. Then there's the age question. Where did 3I Atlas come from? Trace the trajectory backward. The comet entered the solar system from the direction of Sagittarius near the galactic plane. Retrograde orbit tilted 175 degrees relative to the ecliptic, moves almost opposite to planetary orbital direction. Incoming velocity at infinity, 57.9763 kilometers per second. That speed and trajectory tell a story. Marshall Eubanks and team published a paper in August 2025 examining pre-encounter kinematics. They convert velocity vectors into galactic UVW coordinates, U velocity component negative 51 kilometers per second toward galactic center. O velocity component positive 18.5 kilometers per second, upward through galactic plane. That vertical velocity is high, too high for thin disk objects which orbit near the galactic plane. Thick disk stars have those kinds of vertical motions. Thick disk stars are old, 7 to 14 billion years old. Formed during cosmic noon, the period 2 to 3 billion years after the Big Bang, when the Milky Way was churning out stars at peak rate, and the interstellar medium had lower metallicity than today. Matthew Hopkins leads a July 2025 study estimating with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old based on typical ages of thick disk population. The Sun is 4.6 billion years old. 3. I Atlas may be triple that age. Older than Earth, older than the solar system, older than most stars you can see in the night sky. A relic from when the galaxy was young and metal poor and the universe was still figuring out how to make planets. Astor Taylor and David Seligman run independent galactic orbit analysis. They map nearby star velocities and compare them to 3I Atlas trajectory. The comet does not match any known stellar stream. Unlike 1I Oumuamua and 2I Borisov, which have velocity vectors consistent with Pleiades and Wolf stellar streams, 3I Atlas stands alone. It came from somewhere specific, but we cannot pin down the parent system. The galactic orbit suggests thick disk, or the transition zone between thin and thick disk, where old metal-poor stars mix with younger metal-rich ones. If that age estimate holds, the comet formed 9 to 13 billion years ago, cosmic noon, when the Milky Way was a different place. Star formation rates were 10 times higher than today. Supernova rates were higher. The interstellar medium was enriched with alpha elements, carbon, oxygen, magnesium, silicon, sulfur, but depleted in iron peak elements because type Ia supernovae that produce iron take longer to explode. Early thick disk stars show that pattern, high alpha element to iron ratios. If 3I Atlas came from a thick disk planetary system, its composition should reflect that. Carbon dioxide is an alpha element compound. Nickel without iron fits the pattern if iron was scarce in the protoplanetary disk where it formed. But then it drifted for billions of years through interstellar space, cosmic rays bombarding the surface, radiation processing, volatile ices sublimating into vacuum. By the time it reaches our solar system, it is a battered survivor carrying chemical signatures from an ancient alien environment modified by eons of exposure. The high carbon dioxide might be original, might be what is left after everything else got stripped away. The nickel without iron might be primordial chemistry from a metal-poor star, might be the result of selective processing that destroyed iron compounds but preserved nickel organics. Nobody knows for sure because the Perihelion passage happens when Earth cannot watch. October 21st, 2025. 3I Atlas goes into solar conjunction, 13 degrees from the Sun as seen from Earth, lost in the glare. Ground-based telescopes cannot track it. Hubble and Webb cannot point that close to the Sun without risk. For 8 days, the comet is invisible to terrestrial observers during the most critical phase of its evolution. This is the acid test. The term is Avi lobes. Harvard astrophysicist who ranks 3I Atlas 4 out of 10 on his scale for potential technological origin. His list of anomalies grows with each observation. High carbon dioxide to water ratio, nickel without iron, antisolar coma morphology, sunward pointing jets, trajectory coincidentally aligned with the ecliptic plane placing it close to Mars, Venus and Jupiter while being unobservable from Earth at perihelion, rapid brightening exceeding normal comets, an unusual composition suggesting either extreme formation conditions or artificial design. Loeb proposes that if 3I Atlas is a weakly bound natural comet, perihelion heating at 770 watts per square meter might fragment it. If artificial, it might maneuver or release secondary objects. Either way, perihelion is the test. October 29th, 2025 at 11:15 Universal Time. Perihelion, 1.36 astronomical units, 203 million kilometers from the Sun, between Earth's orbit and Mars' orbit. Maximum velocity 68 kilometers per second with respect to the Sun. The comet crosses the critical distance where solar heating peaks and thermal stress maximizes, but space-based solar observatories can watch. Stereo A spacecraft with Secchi HI-1 and Kyo R2 cameras, solar and heliospheric observatory with LASCO C3 coronagraph. GOES 19, weather satellite with CCOR-1 compact coronagraph, polarimeter to unify the corona and heliosphere satellite. These instruments were not designed for comet hunting. They monitor the Sun's corona and inner heliosphere. But 3. I-Atlas passes through their fields of view and they record what happens. Qicheng Zhang at Lowell Observatory and Carl Baddams at Naval Research Laboratory compile the data. Publish a rapid analysis preprint October 28th. The numbers are wild, rapid brightening. The comet's brightness scales with heliocentric distance as r to the negative 7.5 plus or minus 1.0 power. That exponent is extreme, normal Oort. Cloud comets brighten as r to the negative 2 to negative 4 near perihelion. 3. I-Atlas is brightening more than twice as fast. The September to October observations from Stereo A HI-1, Core 2, SOHO LASCO C3, and GOES 19 CCOR-1 all show the same acceleration of light output as the comet approaches the Sun. The coma extends 4 arc minutes across in CCOR-1 images. Approximately 300,000 kilometers. The glow is not just reflected sunlight, it is emission, active sublimation of volatile ices producing vast clouds of gas that fluoresce under solar ultraviolet. The gas is what brightens so fast. Carbon dioxide and carbon monoxide vaporizing in huge volumes. But here is where it gets weird. The color changes. Ground-based observations from July to September show the comet appearing reddish. Spectral slope, 22.8 plus or minus 0.1% per micrometer in the optical range. Reddish tint, typical of organic-rich materials, similar to Kuiper Belt objects in outer solar system comets. Dust scattering sunlight with a red hue from complex carbon compounds baked into the grains. LASCO C3 color photometry near perihelion shows the comet distinctly bluer than the Sun. In the blue filter, 440 to 520 nanometers, magnitude is minus 0.7 compared to clear filter. In orange filter, 550 to 630 nanometers, magnitude is minus 0.4 compared to clear. Redder filters show non-detections. The comet shifts from red to blue as it approaches perihelion. That is backwards. Dust should redden scattered light. The comet's surface temperature, even at 1.36 astronomical units, is far colder than the Sun's photosphere at 5,800 Kelvin. Everything about thermal emission and dust scattering says this thing should look redder, not bluer. The blue color indicates gas emission dominates the visible brightness, not reflected sunlight, not thermal glow. Fluorescence from molecular gases excited by solar ultraviolet. C2 swan bands in the blue range, NH2 bands in orange, cyanide contributing to the green-blue region. The gas production becomes so intense near perihelion that the light output shifts from dust-dominated reflected red sunlight to gas-dominated fluorescent blue-green emission. The reason for the rapid brightening remains unclear. Zhang and Baddams state this explicitly in their preprint. The brightening rate far exceeds most comets at similar distances. Possible explanations include carbon dioxide sublimation cooling the nucleus early in the approach, suppressing water sublimation, then water suddenly turning on at perihelion causing the brightness spike. Or the nucleus structure involving subsurface pockets of volatile ice that breach the surface under thermal stress, or compositional inhomogeneity with different patches of the surface activating sequentially as they rotate into sunlight. None of these explanations fit comfortably. All require invoking special conditions. Loeb posts his analysis October 30th. The unfavorable geometry, placing 3I Atlas opposite Earth at perihelion, is, in his words, a possible hint of design. The trajectory was fine-tuned to bring it within tens of millions of kilometers of Mars, Venus, and Jupiter while being unobservable from Earth at the critical moment. The probability of this alignment occurring by chance is 0.005%, 1 in 20,000, possible. But suspicious. Mars spacecraft see it up close. ESA's ExoMars Trace gas orbiter on October 3, 2025, when 3I Atlas passes 28 million kilometers from Mars. Mars reconnaissance orbiter with high-rise camera on October 2nd from 30 million kilometers. The images show the comet in the Martian sky as it crosses between the planets. Side view of the coma structure unavailable from Earth. Those images have not been publicly released yet, but the geometry gave Mars orbiters the best vantage point during the critical approach phase. The Europa Clipper mission crosses 3I Atlas ion tail between October 30th and November 6th. Distance from the comet, approximately 300 million kilometers from the Sun. The spacecraft is en route to Jupiter. The trajectory intersects the comet's plasma trail. Instruments detect charged particles composition. Data not yet analyzed publicly. ESA's JUICE mission observes November 4th. Distance 64 million kilometers from 3I Atlas. Multispectral composition measurements, infrared and submillimeter spectra mapping gaseous emissions. These spacecraft encounters provide views impossible from Earth. Parker Solar Probe and Solar Orbiter may catch 3I Atlas in their instrument fields of view during low solar elongation periods, but no confirmed observations are reported yet. The comet passes through the observing zone when these heliophysics missions are focused on the Sun, not on comet tracking. The key question after perihelion: did it fragment? Comets under thermal stress can split. See 2019 Y4. Atlas, no relation to 3I, disintegrated in March and April 2020, approaching its perihelion at 0.25 astronomical units. Thermal and rotational stresses overwhelmed structural binding. The nucleus broke into multiple fragments that dispersed down the tail. Hubble images from April 20th and 23rd, 2020 showed the cascade of pieces. C 2012 S1 ISON fragmented catastrophically at perihelion in November. 2013 ripped apart by tidal and thermal forces, leaving only a dissipating dust trail. 2 Borisov shed a small fragment in March 2020 after its perihelion passage in December 2019. 3I Atlas at 1.36 astronomical units experiences lower tidal stress than Kreutz sungrazers that skim the solar corona at a few solar radii. But the intense carbon dioxide outgassing creates internal pressure. If the nucleus is weakly bound, pockets of gas could blow sections apart. If the nucleus is structurally strong, it survives intact, but loses mass rapidly. Post-perihelion observations will answer that question. The comet emerges from solar conjunction in mid-November 2025, visible low in the dawn sky. Ground-based telescopes resume tracking. Hubble and Webb schedule follow-up observations in December. The brightness extrapolated from space-based coronagraph data suggests the comet will emerge brighter than before. 9th magnitude near perihelion based on stereo and SOHO measurements. That is considerably brighter than pre-perihelion forecasts of 11th to 12th magnitude. If it survives perihelion without major fragmentation, the nucleus integrity will be visible. If it breaks up, multiple condensations and expanding debris clouds will appear. The dust and gas production rates post-perihelion will show whether the activity surge was temporary or sustained. The spectroscopy will reveal if the carbon dioxide to water ratio remains extreme or shifts as deeper layers of the nucleus are exposed. November 3rd, 3I Atlas passes 0.65 astronomical units from Venus, 97 million kilometers. Venus orbiters are not positioned to observe, but the close approach perturbs the trajectory slightly. December 19th, closest approach to Earth at 1.80 astronomical units, 269 million kilometers, nearly twice the Earth-Sun distance. Still too far for naked eye visibility, but within range of large backyard telescopes. Magnitude expected around 11 to 12. Diffuse coma with possible dust tail extending toward Virgo and Leo constellations. The December observations will be critical. Hubble ultraviolet spectroscopy to determine sulfur to oxygen ratio and gas emission composition. Webb near-infrared spectroscopy to measure carbon dioxide, carbon monoxide, water, and trace species production rates. Ground-based optical and radio telescopes to track dust mass loss rates and coma morphology. The combination will paint a complete picture of post-perihelion evolution. March 16, 2026, 3I Atlas passes 0.36 astronomical units from Jupiter. 54 million kilometers, closest planetary encounter of the entire transit. Jupiter's gravity perturbs the trajectory one more time before the comet exits the inner solar system. Proposals exist for Juno spacecraft at Jupiter to conduct flyby observations if orbital adjustments are feasible. Distance of approximately 25 million kilometers achievable with mid-September 2025 maneuver. Juno's instruments, near-infrared spectrometer, magnetometer, microwave radiometer, could analyze surface composition, magnetic properties, thermal emissions. Direct close-range data on an interstellar object, unprecedented. But that flyby window passed. September 2025 came and went without the maneuver. Juno continues its Jupiter mission. 3I Atlas will pass Jupiter in March 2026, observed remotely but not up close. The comet continues outbound. By late 2026, it crosses 5 astronomical units, again heading back into interstellar space. Fading from view, cooling down, carbon dioxide sublimation stops, water sublimation stops. The nucleus goes dormant. A frozen relic resuming its billion-year drift through the galaxy, headed toward the constellation Gemini, direction of the star Zeta Geminorum, traveling at 58 kilometers per second relative to the Sun. In a few thousand years, it will be light years away. In a few million years, it will pass through another star system. Maybe. The galaxy is big and mostly empty. Odds are it drifts alone for eons. But the data remains. The spectroscopy, the brightness curves, the composition measurements, the perihelion behavior. All of it locked into observational archives. The James Webb observations, published in the Astrophysical Journal Letters, in September 2025 by Cordner and team establishing the carbon dioxide dominance in trace species. The VLT nickel detections by Rahat Gonkar submitted to Astrophysical Journal documenting metal emission evolution. The Keck imaging by Hugendam showing nickel and cyanide spatial profiles. The stereo SOHO GOES data by Zhang and Badams documenting rapid brightening and blue color shift. These papers and preprints will sit in databases and libraries for decades, while scientists argue over interpretation, natural or artificial. Pristine primordial ice from the thick disk or radiation-processed survivor of interstellar transit, weakly bound rubble pile or solid nucleus. The perihelion passage answered some questions and raised others. What we know for certain. 3. I Atlas reached perihelion at 1.36 astronomical units on October 29th, 2025 at 11:15 UT, moving at 68 kilometers per second. It brightened rapidly with brightness, scaling as heliocentric distance to the negative 7.5 power. It turned bluer than the sun near perihelion, indicating gas emission dominated visible light output. It showed carbon dioxide to water ratio of 7.6 to 1 in James Webb observations, among the highest recorded. It emitted nickel vapor without detectable iron in VLT observations, anomalous chemistry never seen before in natural space objects. It displayed anti-solar coma morphology, with gas jets pointing sunward in Hubble and Keck images. It followed a trajectory aligned with the ecliptic, placing it close to Mars, Venus, and Jupiter, while being opposite Earth at perihelion, with probability 0.005%. It likely originated from the galactic thick disk based on kinematics, with estimated age 7 to 14 billion years, making it potentially the oldest comet ever observed. The perihelion survival or fragmentation status remains unconfirmed pending November and December observations, when the comet reemerges from solar glare. Post-perihelion brightness spectroscopy and coma morphology will determine nucleus integrity and continued activity levels. Comparison to pre-perihelion data will show if the extreme carbon dioxide outgassing was sustained or temporary. What perihelion revealed, not answers. Deeper questions. The chemistry is real. The nickel without iron is real. The carbon dioxide dominance is real. The rapid brightening and blue color shift are real. The trajectory and age are real. The explanations are contested. Mainstream science says exotic natural object from ancient low metallicity star system with unusual volatile composition, modified by prolonged interstellar exposure. Chemistry never seen before, but still natural. Carbon dioxide ice line formation or radiation processing, nickel tetracarbonyl decomposition, structural inhomogeneity driving asymmetric outgassing, rapid brightening from subsurface volatile release, blue color from intense gas fluorescence. All possible, all requiring special conditions, but not impossible. Loeb and a minority argue the anomalies stack too high. 8 distinct oddities that individually are explainable, but together form a pattern inconsistent with random natural processes. Industrial metal emission, anti-solar jets, ecliptic alignment, perihelion timing, rapid brightening beyond comet norms, blue color contradicting thermal expectations, extreme volatility ratio, and thick disk age. He ranks at 4 out of 10 on a technological probability scale. Not claiming certainty. Claiming the hypothesis deserves serious consideration given the implications. The debate continues. The data exists. The comet is leaving. One more thing discovered after perihelion. A soil core will not reveal anything new about 3I Atlas, but the trajectory data allows backward integration through galactic space. Follow the orbital path in reverse. Track where it came from. Not just thick disk versus thin disk, not just cosmic noon versus recent ejection. Specific stellar populations, specific regions of the galaxy. The galactic orbit suggests it has been traveling for 7 to 14 billion years. During that time, it crossed the galactic plane multiple times, oscillating up and down through the disk. Radiation exposure from cosmic rays. Temperature cycling from passing near bright stars and through cold interstellar clouds. Collision with interstellar dust grains. Chemical erosion of the surface layers. All of this shaped what we see today. If the thick disk origin is correct, the parent star system formed when the Milky Way had 1/10 the iron abundance of today. Planetary systems from that era built rocky planets from alpha element-rich materials, magnesium silicates, carbon compounds, oxygen ices, sulfur compounds. But low in iron, nickel, cobalt, the comets from such systems would have unusual compositions compared to solar system standards. Carbon dioxide rich, water poor, alpha element enhanced, iron peak depleted. 3I Atlas carries the chemical signature of that ancient environment. A time capsule from cosmic noon, from the epoch when the universe was 4 billion years old and star formation rates were at their peak, and galaxies were assembling their stellar populations, and planets were forming under conditions different from today. That is the scientific value, regardless of natural versus artificial debate. The object samples material from a formation environment we cannot study any other way. Interstellar objects are direct probes of exoplanetary systems without traveling light years. The comet delivers samples from another star's planetary disk. We cannot go there. It came here. Perihelion, at 1.36 astronomical units, revealed 3I Atlas is chemically extreme, structurally unusual, kinematically ancient, and observationally anomalous compared to every comet ever studied. Whether that reflects bizarre natural processes or something else, the data forces reevaluation of what we think we know about comets, interstellar objects, planetary formation, and galactic chemical evolution. The comet passes, the questions remain. November and December observations will add detail. But the fundamental mystery endures. An object older than Earth, traveling faster than any previous interstellar visitor, outgassing alien chemistry, brightening like nothing else, turning blue when it should stay red, emitting industrial metals, and crossing our solar system on a path aligned with the planets while hidden from Earth at the critical moment. Natural freak or deliberate design, 3I Atlas is unique. Perihelion proved that.